Today, we're talking about something that can literally destroy a network in seconds. And I mean utterly catastrophic failure. We're going to dive deep into network loops, because once you really understand what one does to a network, trust me, you'll never forget why preventing them is so critical. So let me ask you this. What could possibly take down your entire network, not in minutes, but in a matter of seconds, even if you've checked every single cable and everything is plugged in perfectly? It sounds like a trick question, right? But it's a very real threat. The answer? A network loop. That's it. Sometimes it's just a single cable plugged into the same switch, or a few connections that accidentally circle back on themselves. But that simple mistake creates the perfect conditions for a complete and total network meltdown. All right, so let's get into it. To really wrap your head around the solution, you have to understand the problem from the inside out. So we're going to break down exactly how this accidental takedown happens. You know, it all starts with the basic anatomy of a loop. And what's wild is that they're almost always created with the best of intentions. You're not trying to break things. You're usually trying to build a more resilient, more reliable network. So how does this actually happen? Well, imagine a pretty simple setup. You connect switch A to switch B. That's your first link. Then you connect switch B over to switch C. And finally, thinking about redundancy, you run a cable from switch C all the way back to switch A. And boom, you've just created a physical loop, a perfect triangle of connections. And look, on the surface, this seems totally smart. The goal is redundancy, right? If that link between A and B ever fails, traffic can just go the other way, through C. Awesome. But here's the problem. Ethernet itself has a kind of fatal flaw for this design. See, unlike IP packets, which have a time-to-live counter, Ethernet frames have nothing like that. There's no built-in timer to tell them, hey, you've been around too long, it's time to die. So they can just circle that triangle forever. And that forever part, that's where things get really bad. This leads us to the first catastrophic consequence, something we call a broadcast storm. This is the moment a single, tiny piece of traffic multiplies into an overwhelming, network-crushing flood. So, to get what a storm is, you first have to know what a broadcast frame is. Think of it like a public service announcement for the network. It's a device shouting something like, hey, who has this IP address? Or, I'm new here, can I get an IP? By design, a switch hears that and forwards it out of every single one of its ports to make sure everyone hears the message. In a normal network, that's fine. In a network with a loop, well, it's an absolute disaster. Let's just trace it for a second. A computer sends out just one single broadcast frame. It hits switch A does its job and floods it out towards switch B and switch C. Switch B gets it, floods it to switch C gets it, and floods it right back to switch A. It's just made its first trip around the loop. But it doesn't stop there. Of course not. As that original frame is circling, each switch sees it come in on a new port and floods it out again. Now you have copies, and those copies are making their own trips around the loop, creating even more copies. It's multiplying exponentially. And that is the storm. In milliseconds, literally faster than you can blink, that one frame has become thousands, maybe millions of identical copies, all just screaming around the network at full speed, eating up every last bit of bandwidth you have. The consequences are immediate. The CPUs on your switches just spike to 100%. They're trying to process an impossible amount of traffic, and they just can't keep up. They become unstable, they start dropping packets, they might even freeze completely. For your users, nothing is getting through all that noise. The whole network grinds to a halt or just collapses entirely. But a broadcast storm is only one part of the chaos. The loop also causes a second, slightly more subtle problem. It completely confuses your switches about where all the devices on the network actually are. So here's how that confusion happens. A switch learns where devices are by looking at the source MAC address of any traffic that comes in. So when a frame from, say, host X arrives on port 1, the switch makes a note. Okay, got it. Host X is on port 1. But because of the loop, a split second later, that same frame shows up on a different port, let's say port 24. The switch erases its old note and says, wait, scratch that, host X is on port 24. Then it sees it on port 1 again. It just keeps flipping back and forth, constantly updating its table, never actually knowing where host X truly is. We call this MAC table instability. The result of this instability is just pure chaos. When a switch doesn't know where a device is, it basically gives up and just floods the traffic out of every port, which, by the way, just adds more fuel to the broadcast storm we were talking about. This also means that traffic meant for just one specific computer can get duplicated and sent over and over again to that same device, which can cause all sorts of applications to crash or reset. So here's the crazy part, the big twist in this story. After everything we've just seen, you'd think redundant links are the enemy, right? But in any serious network, any business, any school, any hospital, redundancy is not a luxury. It's an absolute necessity. You need to have those extra paths in case a cable gets cut or a port on a switch dies. And this really gets right to the heart of it. The problem isn't the extra cable. It was never the extra cable. The problem is having all of those connections active at the same time without some kind of intelligent system managing them. Basic Ethernet on its own simply cannot handle it. So, as we start to wrap this up, let's just quickly recap the key lessons from looking at the raw, destructive power of a simple network loop. At the end of the day, an uncontrolled network loop creates 3 huge problems. You get these all-consuming broadcast storms that just suck up all your bandwidth. You get MAC address table instability that makes your switches basically lose their minds. And you get a flood of duplicate frames that messes up applications. Put them all together, and you get severe and often total network failure. And this is the bottom line. Without some kind of smart control protocol layered on top of Ethernet, a simple physical loop isn't just an inconvenience. It is a ticking time bomb that can take down your entire local network in the blink of an eye. Which leaves us with a huge question, right? If we absolutely need redundancy, but redundancy without any control causes a disaster, how do you possibly get the best of both worlds? How can we make our switches smart enough to have those backup links ready to go, but keep them blocked so they don't create a loop? Well, that is the exact problem that the spanning tree protocol was invented to solve.